external engagements, including CAPI and OpenCAPI. Over his 25-year career at IBM, Mr. Allison was the chief engineer of various industry-leading IBM chipsets that spanned cache coherent, memory, and node controllers. His experiences in computer architecture and logic design. In his current role, Brian leads the IBM enablement team that drives partner-led solutions, including OpenCAPI, in various ingress, egress, and CPU offload transforms. Let's give a warm welcome to Mr. Allison.
Thank you, Steve. Can you hear me okay? Yes. Like Steve said, we're going to talk a lot about acceleration technologies tonight. Some of them are going to be, let's call it IBM, led, driven, initiated. But I also want to give you some industry perspectives of what's really happening out there. A lot of people don't get the visibility that I do at various trade shows and partnerships and conferences and things like that. And there's a lot of things that are happening that I just want to kind of bring to your awareness. We can start to talk about a few of those things, and then I can kind of whet your appetite a little bit, and then you can go off and do some further research yourself. If there's any questions that you have along the way, you can obviously raise your hand, and we can have this as an active dialogue, or we can do it towards the end. I always like to kind of know my audience. How many folks here are retired? Okay, maybe about a quarter. The rest of you folks are obviously active development engineer type folks, I'm assuming. How many people are actually looking at alternative accelerator technologies to solve some of their workloads, whether it be a GPU, an FPGA? 1, 2, 3, 4. Okay, so about 4 or 5 of you. Okay, all right. So this slide is probably something that most people are pretty familiar with. This is Moore's Law. One of the things that's been happening in the industry over the last at least 5 or 6 years is that, some folks are saying Moore's Law is dead. I'm not so sure it's dead, but it's significantly struggling, right? The days of, okay, I'm going to do a new processor node. The new processor node is going to give me double the density, double the performance every time I go to a new processor node. Those days are long gone. That probably stopped after maybe, 22 nanometer. So what's happening now is you can still get double the density of the circuits, but you're not getting double the performance. And what folks are having to do, if you look at what Intel's doing, right? They're dumping a ton of money into fabs, but they're not getting a lot of return out of it. And it's really whittled down to some leading, fab suppliers, TSMC, Intel, but it's difficult because look at Intel, right? They're struggling to get their 10 nanometer node out. Right, so they're putting a ton of money into that investment and not necessarily getting a lot of return out of it. If you look at the way workloads are emerging, it's a broad spectrum of things. You got artificial intelligence, I call it actionable intelligence. So there's a ton of things happening in the cognitive space. The hyperscalers are doing a lot of things where they need to start looking at their problems differently. Clouds. Right? Everybody's talked about going to a cloud environment. Well, the question is, do you go public cloud, private cloud, hybrid cloud, right? What kind of environment do you go into? And open solutions. One of the things that's kind of amazed me over the last few years is even the national government is going into an open environment. They don't like proprietary software anymore, right? Because once it's proprietary and it gets hacked into, right, you're a lame duck. The more open it is, the more eyes that are on it. And so the guys in the government are actually saying, we actually want to be open source as well, right? And so they're participating in open communities, which totally baffles me. Well, those guys are still probably, running some pretty old code, but they're trying to play catch up. The other thing that's happening is that there's open compute type forums, and there's big industry leaders like Facebook, Microsoft, even Intel, right? They're participating in some of these open initiatives because they don't want to just solve these problems alone, right? So if you go out there, you can go into various forums that are out there, and you'll see these guys participating in all these open standards. So they're all trying to converge and figure out, what's the best way to solve these problems, because everybody has them. It's just in one format or another. System architectures. Von Neumann, right? If you look at what's happening with computer architecture these days, it used to be, okay, I just put a memory subsystem in there, I put a networking subsystem in there, I put a storage subsystem in there. Yeah, if I just glue this stuff together, it'll probably work out just fine. What you're going to find out is that the bandwidth demands from all of these evolving applications is stressing the existing architectures that are out there today. So everybody is looking at acceleration in one way or another. Google is doing it with TPUs. Facebook is doing it with AI. The networking companies are doing smart NICs, right? So if you go out and do a secure transaction out on the web today, you go into HTTPS, guess what? That's done on an FPGA doing acceleration. Inefficiencies of traditional I/O subsystems, device drivers, for instance. There's a ton of software pathline in device drivers. So folks are always looking for more efficient ways in order to move their data around, right? You want to have the most efficient mechanism to move your data from the CPU to network to storage to a GPU to an FPGA, whatever it is, right? And you want to be able to move data back and forth very efficiently. Another thing that's happening that I see pretty relevant is storage class memory. Intel today, right, they've got their Optane storage. They're talking about 3D crosspoint for memory as well. Everybody is trying to chase what the next storage class memory that's going to start to emerge. The reason that is because the only ones that are happy about DRAM today are Micron and SK Hynix, because they're making money hand over fist, right? They can't fill the fab fast enough because everybody wants more memory. But if you can come up with something that's non-volatile, persistent, at a third of the cost per bit, and build up this very large memory footprint with latency that's still pretty compelling compared to spinning disk or NVMe, that's the thing that's going to make a big dent in the data center. So you'll see folks like Samsung, they've got their low latency NAND. You've got Everspin is doing stuff with MRAM. There's a few other, Toshiba's doing some things. So there's a lot of companies out there trying to get their technology up and running, because these are the guys that are going to make a dent in what the data center definition looks like. If you look at networking, another interesting paradigm, right? Today, 10 gigabit, pretty normal. 100 gig, definitely emerging. 200 gig, 400 gig, right around the corner. Right? If you don't have a very balanced computer architecture where you can handle all these ingress and egress rates throughout your whole architecture, there's ultimately going to be a bottleneck. And chances are that's going to be PCI Express. So what you're going to see, and I don't necessarily agree with the curve on the bottom, it's kind of showing that this flattened out for I/O. I don't believe that. Right? I believe that I/O is also having the same similar demands, just like memory is. Any questions so far? Yes?
So is the reason memory bandwidth is decreasing? Oh,
It's increasing,
it's
actually.
increasing, okay.
Yeah, bandwidth per core, that's definitely increasing. If you go out there and look, a good example is like SAP HANA, for instance. If you look at what their demands are for a memory footprint, right, it's increasing exponentially. And each one of these guys wants to get a large memory footprint with as much bandwidth as they can possibly get.
So is it scaling with the increase in cores per chip?
No, right? That's why they're having to look for alternative technologies, because you're not getting the density of the memory footprint, because it takes so many processor pins in order to get that large memory footprint. One of the ways that you can kind of mitigate that is you can start to do like memory buffers, and then you can do something where you can build up maybe 4 times the amount of system memory with half the amount of pins. And so they're doing a lot of things like that. Intel's done that before with some of their memory buffers. The power processors are doing that today with memory buffers. So that's one way of mitigating that, is to go with memory buffer technologies. But then you need to have an interconnect that can handle all of the ingress bandwidth coming from system memory as well. Any other questions? Okay, so we're going to talk a little bit about each one of these areas. So these are some of the example areas where innovation is really coming into play out in the industry. Memory, networking, storage, hardware acceleration. Like I said, there's a lot of folks out there doing specific hardware acceleration, right? Not necessarily general purpose, but targeting very specific workloads. And they're building specific hardware to tackle the problems that they have in hand. And they're willing to spend a lot of money to do it, right? Which is something that, 5, 10 years ago I would have said, not so much. But if you look at an AI game today, for instance, right, there's a ton of companies, like I said, Google, Facebook, even Microsoft, they're looking at AI chips, every one of them, right, for different use cases, but all chasing that same market. I don't want to get into like an IBM power pitch, but one of the things that I think is interesting is that out in the industry, whether we like it or not, Intel is like the 10,000-pound gorilla in the industry, always has been, right? They'll make it go as fast or as slow as they want, right? They've been sitting on PCI Express Gen 3 for over a decade, right? Why? Because they can't, right? So they've basically got 95% of the marketplace, right? They've got all of these guys entrenched in with all their switches and routers and all that other stuff, right? Why would you want it to move faster? Well, what IBM basically did was they said, okay, we need to kick the bear a little bit. So they went to PCI Express Gen 4 and did an implementation first and foremost. Well, it just so happened that over the last few months, AMD also paid attention, and they also developed their next generation of processor called a Rome. If you get a chance, take a look at that processor because it's very compelling. And I'm sure Intel is very much paying attention. What I've learned over the years is that, it may appear that Intel is out. They always get a little lackadaisical when they think they've got the world, like they think they're conquering the world. But when they're under extreme duress, which is where I think they're at now because of their 10 nanometer problems, the problems that they're having with Altera when they bought the FPGA company, they bought an AI company that they haven't had a return on investment either, they're going to start to fix their problems. Otherwise, they're going to get a new CEO, right? I mean, they never had these problems underneath Adalini. So, they better fix their problems or they're going to, but take a look at that Rome processor from from AMD. It's a 7 nanometer node. They're the first ones to get there from TSMC. They actually did something that's pretty innovative. Their cores are all in 7 nanometer and they did all this tiling work for all of their I/O. It's all done in 14 nanometer, right? And it's got some very compelling performance metrics. And they're very much leading the industry now with what their chipsets look like. So take a look at them. What Power did was we basically said, you can always put more cores on a die. You always can put a bigger L2 or an L3, but you're only going to get so much diminishing return out of that, right? So we need to start looking at what are the things that we can differentiate ourselves in. And the attack that they took was to basically look at I/O, right? So we need to have a very rich premier acceleration platform where you've got leading edge PCI Express Gen 4, you've got the leading edge NVLink. So for the folks that are participating with GPUs, right, there's an NVLink technology that allows them to do GPU to GPU connectivity running at a 25 gigabit signaling rate. IBM has a relationship with NVIDIA where we can actually do processor connectivity to the GPU also running at 25 gigabit. So what that means is you've got a very balanced system when you have all the interconnects all running at the same frequency. So we've got a number of lanes. We've got 48 lanes of the NVLink technology talking to the GPUs. So that'll talk to the Volta GPUs. So if you're familiar with the V100s, that's the GPU that the power processor can talk to. Now, one of the other things that's happening that I'm seeing is that NVIDIA is not going to just sit there and say, hey, we're going to do this GPU for training, we're going to do this GPU for inference. If you look at what they're doing with their Turing architecture, the T4s that are coming out, if you look at the flops on that animal, right, it's very compelling. And they're very much saying that you can use the same GPU for training and inference. And the numbers are pretty much stacking up. So if you look at that GPU, it's a lot lower cost than like a Volta, and it looks very compelling. So it's very interesting. The other thing that I'm seeing is that, NVIDIA, they had some problems recently with some of the Bitcoining stuff. That's why they were down a little bit. But if you look at some of the other segments, they're making some significant inroads in that. If you ever get a chance to look at what they're doing in their DGX boxes, right, for what they're putting in for density form factors for GPUs, it's something that's very interesting, so I recommend that. The other things that we're doing on the processor chip within IBM is we basically said we're going to do on-chip acceleration. We're going to do acceleration technologies revolving around something called OpenCAPI, and we'll get to that in a minute. We're doing, like I said, NVLink 2.0. So what we did, just by happenstance, not by happenstance, but NVLink 2.0 is basically an Ethernet PHY. Right? It's a OIF CEI 28 gig short reach standard. So what we did with NVLink 2.0 is we basically used the same PHY for OpenCAPI, right, to provide a high bandwidth interface into acceleration technologies where you can do something on like a semi-custom ASIC or an FPGA or something like that. We'll talk about that in a little bit as well. But this is where you're going to start to see a lot of these processors. Intel is going to start to do the same thing. Very interesting. Intel, within the last couple of weeks, there was some press about them buying Mellanox. Not necessarily good for the industry. If that happens, then the only smart NIC left in town is Marvell. But stay tuned on that. There's also some news that Xilinx might buy Mellanox as well, so we'll have to see what happens there. Okay, HPC space. I got a couple of slides on this. One of the things that's happening in the GPU world is that there's something called unified memory address space. So what that means is that GPU memory and system memory, it all works in the same unified memory domain, which is basically the same things that we're doing with our acceleration technologies as well. If you look at NVIDIA P100 with NVLink 1.0, which is what we had on our Power 8 processors, right? The system memory and the graphics memory were actually running in separate domains, right? You actually had to have a driver to move the data back and forth between those two, right? And we could run 40 gigabytes per second. That was a 20 gigabit signaling rate back in Power 8. In Power 9, right, with that unified memory address space, which is what happened with NVLink 2.0, right, that's a 25 gigabit signaling rate. So what you can do now, there's 48 lanes of NVLink connectivity on a processor, right? You can put 24 to each GPU on the top one, right? So you get 75 gigabytes per second. Or you can run 16 lanes if you run it in a 6 GPU configuration. These on the right-hand side, these are the systems for the NAT, a 4 GPU air-cooled system, and the other we had a 6 GPU water-cooled system. These configurations are the configurations of that box for the systems that we deliver to the national labs. Now, if you'll note, right, most of the flops, right, if not all the flops, right, are in those configurations are all because of the GPUs. Make no mistake, right? Jensen, he put $1 billion into CUDA development. He's reaping the rewards for it. It's no longer just a gaming processor anymore. What I did here is I just basically put up what our AC922 looks like. These are the national lab. This one happens to be the air-cooled version, right here and right here. So, this is the system that we put into one of the national labs. The other is 6 GPUs. The other thing that's happening is if you look at what's happening in not only the GPU market, but also in the FPGA market as well, they're all going high bandwidth memory, right? So they have all this local memory. It's not a ton of it, but it's very high bandwidth, right? It runs over a gigabit signaling rate to these HBMs. And so they have like 16 gigabyte and 32 gigabyte variants for the GPUs. The FPGA guys are doing the same thing. If you look at the high-end FPGAs, those also have HBM as well, right? So what you want to do is you basically want to move your model from system memory down into HBM memory, and that's where you do all your crunching, right? So that, all these guys are basically following the emerging standards of what's happening with memory. And these guys happen to do it with HBM. Some of the other GPUs do it with GDDR. These guys are doing it with that. This is what I wanted to kind of show on this was I mentioned this earlier. The Power 9 CPU is the only processor that's out there that you can actually do NVLink connectivity between the processor and the GPU. All GPUs today can do NVLink connectivity running at 25 gigabit running between them. Power is the only one that you can do it from the power between the processor and the GPU. If you do this on an Intel box or anywhere else, it's always PCI Express. Ultimately, this will be your bottleneck here, right? So you'll be very efficient here, but run into a PCI Express Gen 3 actually still here. They haven't even gone to Gen 4 yet. So it's pretty much an imbalanced memory interconnect, or not memory interconnect, but system interconnect when you've got PCI Express there. I just wanted to kind of mention that. How many of you guys are playing with CUDA today? You two guys back there are probably doing CUDA work, right? Yeah. There's a couple of things that are happening in the industry today as well. IBM has basically taken an initiative where we don't think that everybody has to be a data scientist. We want folks to be able to use, open source frameworks, but be able to manage them very easily. Take advantage of some of the capabilities that IBM has as far as large model support and a couple of other things. There's something called Power AI Enterprise. If you've been following the press over the last week, there was an announcement last week at IBM Think where they talked about Power AI Enterprise merging with IBM Watson machine learning for acceleration. If you get a chance, you should go ahead and Google that and go ahead and read the trade on that. So what they're trying to do is sync up together with all of our software techniques that we did with Power AI Enterprise, along with all the hardware that we've put together like I showed on these previous charts. So what they did was for these systems right here, they basically built a framework where you can manage it very easily. So in other words, they don't want everybody to be a data scientist. They want folks to very easily, through IBM SpectraConductor, manage their environment, manage their cloud with Spark. They want you to be able to do hyperparameter tuning when you do backwards propagation very easily. They want you to do things like distributed deep learning, which we'll talk about here in a minute. But they want you to be able to label, train, and deploy your environment in a matter of hours instead of weeks. That's the goal. So the idea is you've got all this data, you got all these images. You might have a traffic scene, for instance, and you want to label all of the red cars going through a traffic scene. What you can do is you can take your image, all of the images that you have, take a very small subset of the images, label a few of them, then run it through an automated process where it'll go off and auto-label all the rest of the images for you, right? Then you'll do that recursively because it still makes some mistakes. But it's a lot easier to do that than to label a million images, right? That would be very time-consuming. Then the ability to train and then deploy and then have it work on a converged cloud environment, whether the cloud environment's x86 or whether it's Power, it can manage both of them. And then it can basically do that with all of these frameworks. So it does TensorFlow and PyTorch, Chainer, things of that nature. Any questions so far? Is this too deep?
I'd rather it's deep than shallow. Go ahead, keep going.
All right. This is not necessarily an endorsement, but these are just some of the examples of the things or the problems that people are trying to solve. Right? So what this is called, it's called large model support. I mentioned this earlier. The ability to move data back and forth between system memory and GPU memory with a very high bandwidth interface without using a driver is something that's very compelling. So they did an experiment where they did a GoogleNet model with this ImageNet data set where they ran it against a Xeon x86 cluster of 4 V100 GPUs running behind PCI Express Gen 3. Then ran it against that same server that I showed you earlier with the V100s running NVLink. They took this same model of 1,000 iterations, so that was your batch size. On the x86 platform, it took about 3 hours to do, so that's your morning, right? That's what it took on a Xeon-based platform. Well, they basically did the same iterations again, and it ran over a lunchtime, right? So those kind of performance metrics make it very compelling when you start to get turnaround times where you're getting answers within lunch times instead of days. This is another one that's pretty intriguing. So our Zurich researchers did a number of different, let's call it software optimizations, where they looked at how the data was being moved around a cluster and drove some efficiencies into those data movements. And then they worked on some of the algorithms as well. This distributed deep learning is basically a package that's underneath Power AI Enterprise. It's this guy right here. What it allows you to do is it allows you to basically scale up to 256 GPUs. And this is what they've done with an actual configuration. So they actually took a ResNet 101 layer set of, what's the word I'm thinking of layers of a problem. They also did with ImageNet with 22K layers, right? And they took it, one system, right? And then they basically clustered it to 64 systems, right? And they took something that took 16 days to train, right? And got it down to 7 hours. So something that took a couple of weeks to actually do the training on this particular data set now only took a day. Now they actually built up a cluster of these servers in the lab, and they ran it, and it got to, they actually did a cluster of 256 GPUs, and with these software optimizations that they put in place, right, they did it again with a ResNet with 50 layers and ImageNet with 1K layers, they actually got 95% of the scaling, which is pretty remarkable. Now, they actually don't think there's a limit on the software itself. They're actually going to try and do this same type of scaling on those servers that we deployed at the national labs and see how well it still scales. But this is one of the big problems that's out there. So if you look at the NVIDIA DGX boxes, they have 8 GPUs in them. The question is how well do they scale, or do they not scale, right? So if you can actually build up a cluster, right, using InfiniBand as your cluster interconnect, right, and build up a 256 GPU cluster and get it to scale like this, that's some good stuff. Hyperparameter tuning. It's said that about 80 to 85% of the time that data scientists spend is actually in labeling and doing hyperparameter tuning, right? This is where they spend all their time. Now, what happens is that when the data scientists do all of their hyperparameter tuning for all their backwards propagation, right, when they're doing their supervised learning, they run hundreds and hundreds of jobs to figure out the right weights, right, for their hyperparameters. The problem with that is that it's very labor intensive. You have to go through and figure it out and figure out which ones is giving you the best results. Now, there's actually a feature within Power AI where they have this auto tuner where they kick off like tens of jobs, and using a couple of different approaches, random, tree-based, partisan estimators, Bayesians, right? They've got a couple of different approaches where they'll do the hyperparameter tuning recommendations for you. So the idea is that by the time you come back and look at the results, we'll give you the best guidance on what hyperparameters you should use, which is very intriguing. That's my GPU spiel. We're going to take it over into like FPGAs and semi-custom ASICs and other things. Any questions so far? I'm blowing a lot of information your way. Hopefully this is okay. Okay.
I got a question.
Sure.
So a lot of the acceleration that you're claiming here has to do with automating some of the tuning.
Yep.
So that really doesn't matter what hardware you're running it on.
No, it does, because there's a couple of different things. These software optimizations are not tuned for x86, right? It's tuned towards a power-based platform. That's one. The second is that the...
If I'm looking for red cars and images, who cares what the processor is?
not necessarily the processor itself, but you know, you're still going to ultimately run into the limits of what the box can do for you. Yes, you're right. The techniques on like labeling and running and stuff like that, you can do that on any platform. But you're not going to get the performance.
Do you have a sense for what the percentage is, the very cool things your software guys at IBM have figured out?
Yep.
And what percent of this acceleration is due to hardware?
So all of these, this slide here is all software techniques. Okay, that's what that one's meant to show. This one is hardware-based, totally hardware-based.
Thanks.
Okay. How many folks have been thinking about maybe solving or tackling some of their acceleration problems with FPGAs? Not a one.
Oh, I have customers that do it.
Okay, you're a good candidate then. So, because not everything is meant to run on a GPU, right? There are certain problem sets where either the algorithm is changing enough, it needs to be tightly parallelized, or it needs to be gate level mapped or optimized, right? And there's a number of different, let's call it problem sets, where folks are looking at FPGAs as alternatives to GPU.
There's this outfit called the Maryland Procurement Office. It buys a lot of FPGAs to use.
Government?
Didn't say that.
Okay, got it. One thing that's happened over the last 10 years, maybe a little bit longer, is FPGAs have become really relevant in my mind. When I first started in my career, the only thing that FPGAs were really good at was like power control, sequencing, that kind of stuff, right? It was very rudimentary type of things that you could do in an FPGA. Nowadays, what you're going to find is that Xilinx, they're using the latest processes from TSMC, right? They're going very cutting edge technology, and they've got all of the industry standard interfaces that you can think of on an FPGA, right? Whether it's PCI Express, whether it's Ethernet, whether it's storage interconnects, what have you, right? The densities of the circuits that they're able to get on the design, plus the industry standard interfaces, with being able to run at maybe 500 or 600 megahertz, makes it a compelling alternative to a GPU. The other things that happen too is that not everybody wants to line NVIDIA's pockets, right? People want alternatives. People are also, as an aside, people are also starting to look at what AMD is doing with their GPUs. It's very interesting. Over the last couple of years, maybe the last 18 months, if you look at the inroads that AMD has made with their GPUs, take a look at them. They're starting to play catch up. So they're starting to see some very compelling results with what they're doing with their GPUs. One of the things that we looked at were FPGAs is not everybody wants to be a Verilog or VHDL designer, right? There's a significant amount of corporations that are out there that have C and C++ designers or code writers, but not Verilog or VHDL. There's a couple of those, but you probably got hundreds of guys that are writing code. One of the things that we've done at IBM is we've created what I would consider a high-level framework where guys can do C or C++ or Go programming languages, and you can run it through a hierarchical level synthesis, which is Xilinx's compiler, and run it through their tool chain to create a bit image for an FPGA. And so we've actually spent a significant amount of time using some of our historical acceleration interfaces for CAPI 1.0 and CAPI 2.0. But, at the second half of this year, we're actually going to have, we're going to actually have an OpenCAPI variant of this a little bit later this year. Yes?
What are these acronyms? CAPI and SNAP?
So CAPI was Coherent Accelerator Processor Interface or Interconnect. Okay? So what that means is that we actually created an architecture where the accelerator on an FPGA is running in the same coherent address space.
Is that an IBM thing?
Yes. But I'll put a caveat to that. Xilinx is also attacking the same problem through CCIX. So there's 3 industry accelerators that are being initiated in the industry today. One is CCIX, being driven by Xilinx. The other is Gen Z, which is being driven by HPE and Dell. And then there's OpenCAPI, which is being done by IBM. CCIX is basically putting coherency on top of PCI Express. Because PCI Express today is a non-coherent interconnect. Everything is a read with no intent to cache or a DMA store, for instance. They added 2 protocol layers onto PCI Express and added coherency into PCIe, right? And they're which makes sense. And the reason that they're doing that is they realize that we've got a 90 or 95% install base. Why wouldn't I just put a couple of protocol layers onto something that's very much indigenous in the industry today? The only problem with that is, again, you're being mitigated by Intel driving PCI Express. And the second is it's not going to be optimized for latency because PCI Express is, for lack of a better word, bloated, right? Because it has all these backwards compatibility and all these other things. It's got to support Gen 1, Gen 2, Gen 3, all these other different things. And then you put 2 additional layers on top of it, you've added additional bloat. HPE and Dell are attacking the industry through Gen Z. They're basically doing a fabric switch topology, where what they want to do is they want to do rack-to-rack and server-to-server type fabric acceleration. Okay. And then what we did with OpenCAPI, which we have a few slides in a little bit, is we went to address acceleration within the server. Now, one of the things that we did was we basically said, to get back to CAPI, SNAP stands for storage, networking, accelerator, forget what P stands for. Drawing a blank. What we wanted to do, though, is we took a number of different open source C++ examples, OpenFOAM, for instance, MetalFS, a few other things. We got them off of GitHub and said, okay, if I took these open source pieces of code, right, could I get those to actually run through our framework and build a bit image and run it on an FPGA, and how long would it take? If you're actually going to do something where you did it at a Verilog level or a VHDL level, chances are it'd probably take you 3 to 6 months to do something like that. It's not trivial, right? There's only so many skills that go around with that. We actually took some open source examples and we actually got them running in 3 days. And we had it performance optimized in like 10 days. So we took things that were running on a CPU thread, right, trying to be run on a core, offloaded them onto an FPGA, right, ran it through a, offloaded those same algorithms onto an FPGA, parallelized them like crazy, right, and see how far we could stretch it. And we were basically saying that, you know, anywhere from like 10 to 30x results, depending on what the algorithm was. But the key is that you're doing it in days and not in months.
How efficient is it?
As far as what, very efficient from that. It kind of depends on which application you're running. But like I said, we were seeing, you know, depending on, like I said, the application, we were seeing results of, you know, you could do 10 times the amount of work, or we've seen results where it might just take 10x less time, depending on which one that you're doing. And so this is something that I always, you know, we actually could spend a couple hours just talking about this in itself. And so we're actually having education classes through academia work groups and things of this nature to teach people how to do FPGA programming more efficiently than at the Verilog level. And the way that it looks is, you know, you basically got your actions that you're focusing on, and Snap itself is doing all of the heavy lifting of how do you hook up your memory? How do you hook up your PCI Express? what's your memory interconnect going up to that bus? How do you manage it? How do you do all of your queuing, right? So you worry about the action that you're interested in accelerating here. We take care of all the rest of the framework. And you just focus on your whatever you're trying to offload. Questions so far?
How would it, if you had those two methods, which one would cost more?
What are the two? Sorry.
Well, an FPGA implementation versus a stock CPU implementation.
In my mind,
I would guess the stock CPU.
yeah. I
would
mean,
be the-
CPUs in my mind are commodities anymore.
Yeah.
Whether we like it or not, they are.
Yeah.
The problem with CPUs is they're only going to take you so far,
Yeah.
right? Because they are general purpose type, environments, right? You're only going to get so much performance out of them. And there's certain algorithms that don't run very efficiently on a CPU. But you could tailor your FPGA to basically tackle that problem specifically. There's a lot of problems like encryption or compression, SHA-type algorithms. I mean, the CPU could be better purposed for other things, and then you offload those type of algorithms onto an FPGA and target those ones specifically.
So it's, probably ideal thing is a hybrid type of thing.
That's exactly right. And that's what you're going to see moving forward more and more. I mean, Microsoft is doing it today. Amazon is doing it today. If you look at the cloud environments that they're putting out there, they have a variant of components. They've got FPGAs, they've got GPUs, they've got all of those things because the heterogeneous environment is where the industry is really going, right? Because each one of them wants to participate in its own way. Each one has efficiencies that the other ones don't necessarily don't have, right? And so you're going to see those type of environments become more and more prevalent as time even moves forward. Okay. All right. OpenCAPI. So we'll talk a little bit about this. I mentioned the 3 consortiums today that are addressing acceleration other than a GPU type environment. There was an initiative done between it's IBM, AMD, Google, Micron, Mellanox, Xilinx, where we came forward with an accelerator architecture that's open and agnostic. So what we did is we basically came up with an architecture. Power was the first processor family to adopt it, but if you look at the architecture specifications themselves, AMD or ARM could implement them if they chose to do so. They're not power specific. So we basically targeted acceleration through an open agnostic way. And a consortium was born out of this particular architecture. I mentioned earlier, the PHY that we use for NVLink connectivity between the host processor and the GPU is the same PHY that we use for OpenCAPI. It's very high performance. There is no device driver. So because what we ended up doing, like we talked about earlier with GPUs where you have unified memory, we have the same concept with OpenCAPI. OpenCAPI accelerators use the same virtual address space just like any other host side application. So there's no device driver to move things between user space and kernel space. Everything is virtualized. So what ends up happening is the accelerator on the FPGA looks like a hollow core to the processor. That's what he looks like. And so the accelerator uses the processor's page and segment tables to do all the translations. He never gets a physical address, so he can never basically corrupt a machine or anything like that because he doesn't have access to any kind of physical media that's out there in the physical, he doesn't have access to any physical addresses where he could corrupt anything. If he does something that's not copacetic, he's going to get a fault or a translation miss or something like that. The architecture it's very low latency, it's very high bandwidth. We basically said we're going to use an Ethernet standard as our interconnect because we don't want to be driven by Intel. We don't want to wait for PCI Express to catch up. We're running at a 25 gigabit signaling rate today. We're looking at 32 gigabit within our Power 10 processors, and even 50 gigabit beyond that. The reason that you have to do that is that a lot of these emerging technologies, whether it's on the networking side or what have you, they're not slowing down. They're going to 200 and 400 gig E just as fast as they can, and you have to have an interconnect that can keep up with them. Or ultimately, it's going to be a bandwidth limiter. I mentioned this earlier. It supports, in my mind, a very heterogeneous environment. Because the reason I say that, how much should I get to this one slide? Is we look at basically all the various components within the computer, right? Whether it's an accelerator that's out there, whether it's a network device, whether it's an advanced memory, whether it's a storage controller, standard system memory, all of these different interconnects can be based off of the same architecture. And since these are all operating in the same virtual address space, to move data from one media to the next is very efficient because you don't need a driver in order to do it. This is kind of a pictorial diagram that I just kind of like to show people so they can kind of get their head kind of wrapped around it. This is a processor core. This is some sort of accelerated OpenCAPI device. This device memory that's sitting behind this accelerator is working in the same domain as all the processor caches and system memory. It's coherent, right? So this memory that's out here looks like just like any other memory that's either in a cache domain or whether there's any kind of DRAM or storage class memory that's out there. So what we're doing is we're looking forward, and the rest of the industry is also doing similar things, is you've got standard system memory today. The problem with doing something like this is very expensive because it takes a lot of processor pins to build up a large memory footprint using standard registered DIMMs, like thousands of pins. So when you got a processor module that's like 60 millimeter by 60 millimeter, it's very expensive to fab that animal and to test it and things like that. So your yields are very poor. So what you do is you actually come up with memory buffers, right, where you use OpenCAPI as your interconnect to a memory buffer, and then you put your registered DIMMs behind it. What this allows you to do is to build up a much larger memory footprint with half the amount of pins. Now all of these different domains, whether it's this memory here, these caches here, this memory here, this memory here, this all looks like a flat memory space to OpenCAPI. Just looks like different memory. Now obviously there's different latency characteristics talking to this guy versus these other guys. You just need a hypervisor to basically manage these things. For the things that are hot pages and things like that, you're going to want to keep them here. For things that are not necessarily or cold or don't necessarily need the latency optimized type applications, you can put them out here. I always like to kind of bring up these charts just to kind of, get you thinking a little bit about where I think acceleration is moving forward in the industry. I mentioned to you earlier, we're actually IBM is having discussions with a number of different memory providers about doing memory chips. We're actually going to standardize OpenCAPI and JEDEC to be a memory interconnect for memory buffer development. So that way other folks can take advantage of the technology there as well. I also mentioned these different storage class memories that are trying to emerge, RERAM, MRAM, ZNAND, right? A lot of guys are spending a lot of money to figure out what the next de facto storage class memory is so they can be an alternative to DDR4 and DDR5. The ability to tier memory, right? And still be able to do load store semantics. So these are not block memory, but it's load store. So from a processor application perspective, he doesn't know whether the data is coming from here or whether it's coming from here, right? It's just load store to him. All right. Memory transform. So these are some different segments where I think you're going to, where folks are doing using acceleration technologies, natural language processing, sentiment analysis, anything that's actionable intelligence, right? It's the guys that know how to harvest their data and actually can make some sense out of that data. 80% of the world's data is actually sitting behind somebody's firewall. doing nothing, and it's all dark, right? The guy that can actually take their data, harvest their data, and make some efficient decisions with, right, and actually do some really intelligent decision makings with that, those are the guys that are to be successful. That's why you're seeing guys like Microsoft, Facebook, all these guys, they have data galore, right? Whether you like it or not, they're going to harvest your data. It's theirs, right? You let them have it. They're going to do something with it. Egress transforms. So the idea is to basically put your accelerator right where it needs to be the most efficient. And a lot of them are not close to the processor. They're actually on the edge of the data center. So as your data is moving from the processor chip and it's moving out into the network or moving into storage, you can actually do this encryption or compression or erasure code in real time. These are some of the things that are happening with these FPGAs or these semi-customs today, is you can actually run this stuff in real time. It's not store and forward. Ingress transforms. You see it today. If you look at a Mellanox adapter or a Cavium adapter, guess what? They've basically prototyped a lot of their smart NIC functionality in an FPGA, got it to work, got their algorithms to be as efficient as possible, and then they harden them into an ASIC. They basically prototype the hell out of all of their stuff in FPGAs, right? And once they want to get into the economies of scale, they'll harden them, right? That's what they're doing. So things like network security, DPI-DK, video encoding, high-frequency trading. The high-frequency trader guys, for instance, they like OpenCAPI because it gives them the lowest amount of latency that they've ever seen compared to PCI Express. It's like a 5x improvement. And it's got very low jitter, which for high-frequency traders, every time you get a very deterministic answer, that's what they want to see, because obviously if they make wrong calculations, that means dollars and cents when you're doing things in the high-frequency trading market. Needle in a haystack. Like I said, you've got terabytes of data, megabytes of data are interesting, the rest of it's junk. So what do? You actually look at all the needles in your haystack as soon as it enters into your server, right? Throw the rest of it away, send around the needles, and get rid of the rest of it. I just kind of wanted to throw some things out there as far as FPGA cards that Xilinx is putting out there. This is Alpha Data's cards with Xilinx FPGAs, but the thing I wanted to kind of mention was these guys are very cutting edge as far as technology. Xilinx's next emerging node for what they're doing, 7 nanometer TSMC, right? Just like what AMD is doing with their processors. They've got HBM memory. They've got PCI Express Gen 4. They've got OpenCAPI. They can support up to 100 gig E, right? If you look at the amount of logic elements that are on an FPGA today, it's almost mind-boggling. They're huge. So the amount of discrete logic that you can put in an FPGA, or even the amount of memory elements that are on an FPGA today. For instance, this one has quad QSFP, Ethernet cages on here, right? Going to a very large FPGA with HBM memory. Very compelling as far as the technical capabilities that you can put on an FPGA these days. I mentioned this a little bit earlier. OpenCAPI today, these are just some lab results I wanted to throw out there. We support a 25 gigabit signaling rate. It's a by 8 implementation. We get a little bit north of 22 gigabytes per second. Very compelling bandwidth measurements that we're observing. PCI Express, if you're getting a little north of 12 gigabytes, you're doing well. Let's see here, where else do I want to take this? A couple of things just to kind of pay attention to before I close this out. It's probably not a bad idea, right, to look at what Intel is doing with 3D XPoint with their Optane drives. They've been positioning them as storage to begin with. They're starting to talk about those with memory. There's other industry initiatives to do something alternative to what Intel is doing. Intel's been showing a lot of press releases around it, but no performance results, which is kind of interesting. They've been working on that thing for a number of years, but they still don't have any metrics that they can show yet. But folks like SAP, with what they're doing with HANA, really are interested in doing these large memory footprints with these emerging storage class memories. Okay, that's actually the end of my slides. I kind of fire hosed you with a lot of information. But I kind of wanted to give you a feel for what IBM is doing a little bit, what the industry is doing. There's a lot of things happening out there that are very interesting. You could basically spend your whole day just surfing the web, and it's pretty cool. Any questions or comments or anything you want to bring up? Yes?
The ratio of standard scalar processor to accelerator seems to be application dependent.
Yep.
Peak performance.
Yep.
So the example you showed with the two accelerators was for just a large system at a national lab. So that may be good for their application, but what about general purpose systems that sell people that don't know what their application is?
You know, it kind of depends on what application you're running. But let's take the cognitive, let's just say like machine learning or deep learning. There's a number of industry partners, and NVIDIA is doing this as well, where they're trying to position their GPUs, for instance, where you could scale anywhere from 1 to 16 into like a box, right? And they're trying to build a Swiss Army knife of environments where you can come in and buy a single GPU and start to do kind of your application acceleration running at a very small scale. Worry about getting it tuned to what you're expecting and then scale from then on. There's a significant amount of people that probably, you know, if they did a very minimal amount of acceleration, that would be just fine for them. But then there's the guys that are playing in the HPC space that need a ton of horsepower, where they're looking at scaling, you know, into many, many petaflops. And so they're looking at scaling where it's more accelerators than CPUs, because the CPU is just basically an orchestrator, right? He's basically helping you manage the data and move some things around, but most of the horsepower is actually done in the GPU. So I think there's a fine line, and that's where I think most of the homework has to come into play. Is you need the guys that understand their applications and figure out if there's certain inefficiencies that are at play today, and if there's other alternatives to get around those efficiencies or inefficiencies. The days of just stacking up servers, clustering them over a networking fabric is just, it's only going to take you so far. And it gets expensive to do that because, you know, you're building a large data center and you've got racks and racks of servers and storage and managing all that stuff. If you could do an optimized solution where you did a TCO assessment where I said, you know, I've got 8 servers, and if I, you know, just put a couple of GPUs or an FPGA into a single server, right, and start to consolidate things, I think those are some stories that you know, need to be told, and I think that's happening. Like I said, scaling just for the scaling of doing it through a CPU, yeah, it might be good for some applications, but if you want to kind of make that next, let's call it, you know, leap, right, you're going to need to start looking at alternatives like that. Does that make sense? Okay. 'Cause like I said, there's like, you know, mom and pop kind of stuff, right? They might be happy, you know, he owns a grocery store or whatever. He might be happy with just having a couple of racks or a couple of servers or whatever. But once you kind of get into even what people are doing over at Mayo, we've got a number of folks looking at, you know, images, right? So if you look at oncology or the cancer centers, and, you know, you've got all this data, right, now. You've got a huge privacy problem, right? What do you do with all this data, and, you know, how much can I harvest of it? But you have so much data out there that probably could be analyzed to look for abnormalities and things like that through deep learning techniques, where if you could take out, you know, 90% of the you know, manual inspection of X-rays or MRIs and have a machine do it and only bring up the interesting stuff to a clinician, right? I think those are things that are very interesting in just about every, you know, spectrum of the industry that's out there. But like I said, especially in the medical industry itself. I mean, the privacy laws are kind of interesting, and how do you share data amongst all the different institutions and things like that. And so I know they've got a lot of things they got to work out with respect to that. Yes?
Would you happen to know what portion of IBM's business is related to systems like you're talking about? That business, high performance computing.
It's the systems
Now and in the
business is
future,
not what it
too.
used to
Yeah,
be.
yeah.
Let's put it that way. There's multiple things within the systems business. The Z mainframes are still doing pretty well. So every time they do a new release of the Z mainframe, and there's a new release, the MIPS goes up significantly, and then there's always a refresh cycle amongst all the banks and all those guys. So those guys are still making a significant investment in the mainframe. In the power business, the margins are still pretty good in the AIX, IBMI space. There's still a significant number of folks that are, playing in those domains. In the Linux environment, though, those margins are relatively modest. And then if you look at what drives revenue within systems, pure systems, let's take power for instance, it's not in the processors. That to me is becoming pretty much a commodity. You got to keep up with Intel, right? You got to stay even, because otherwise it's just a hard argument to have if you're not at least playing in a level playing field. But there's still significant opportunities in memory and storage and services and software in all those different domains. If you looked at IBM's reports and stuff like that, the portion of the business that's purely driven by systems is a relatively small number compared to what they're doing in the cognitive space, what they're doing in the cloud environment, what they're doing in certain other software type environments. So yeah, it's no longer the 20 years ago that was the cash cow of the business. It's not so much that anymore. So, did that answer your question?
I don't know if it answers it or not.
I don't know. I don't have specific metrics to give you.
Yeah,
Per se.
I was saying, if you can tell me if you address this or not.
Sure.
Because I can't tell. The technology you describe,
Yep.
to me, is current technology for a selected set of applications.
Yep.
I don't know what they are. Maybe it's weather forecasting or
There's
deep
stuff like that.
learning
The
or,
weather company is doing stuff. Yep.
Oceanography,
Yep.
global
Seismic
changing,
stuff.
Yeah.
I think what you're going to see. Yeah. Let me. Yeah.
And I want to know what portion of that
Yep.
is of IBM's total revenue.
Yeah.
Or is it? I think it's probably a small part.
I think.
But I
Yeah. Let
think
me
in
kind of
the
answer
future it
that
might
in
be
a couple of
bigger.
different ways.
Yeah.
If you look at what IBM delivered to the national labs,
Yeah.
right, for Summit and Sierra, the GPU portion of that was very significant. It was by far the biggest, attributed to those servers. I think if you look at FPGAs, that's very small, very, very small. I think it's going to start to get some more inroads moving into the future, but right now it's relatively small. I think GPUs in general, I think are very relevant across the board. Right? I don't know what the numbers are, but I think because of the relevancy of the different areas in which it can participate, because there's so many different applications that can make use of them, I think that has. But the problem with the GPUs is that IBM doesn't make any money on the GPUs. Most of that money is going into NVIDIA's pocket, right? Because we're not developing it. And whether we like it or not, NVIDIA, they have a captive market today. And so, it's, they're doing very well. But they should, though. I mean, Jensen invested $1 billion into developing CUDA, right? He took a chance, right? It was a gaming thing, right? Historically speaking. He realized it worked well with other certain workloads, and he made a big bet and it's paying off. But I think what you'll see out there, especially in the HPC space, GPUs are extremely relevant. Everybody's using them.
Yeah.
Other spaces, probably not so much. General purpose stuff, probably not so much. But HPC for sure.
Okay, thank you.
Any other questions?
Take one more. We're good? Mr. Nealon?
I'm not sure how to ask it, but IBM.
I don't know how to answer it then. No, I'm just kidding.
IBM has done a number of attempts at leading industry directions.
Yeah.
That haven't been too successful.
Yep.
I can think of a few.
Yep.
It sounds like this OpenCAPI is another, I mean, not that it's not a great idea, but people don't tend to jump on the IBM bandwagon. And I'm just curious how people are responding.
It is true. How do I say this? So, chances are if it's an accelerator technology that, let's call it like an OpenCAPI architecture, because you always have to get past the Intel argument first, right? That's always step number one. Once you kind of get into the, okay, I understand what power is, I know what the value of going to power is, then the next set of conversations can happen. Then you actually have to get over the vehicle of, or the hump of, well, why would I do OpenCAPI over PCI Express? Right, that's the next set of conversations that you have to have. Again, the HPC guys eat it up like crazy. High frequency guys as well. General accelerator developers, not so much. They'll pretty much stay on PCI Express and be happy with those. If IBM is the only processor vendor to adopt OpenCAPI, you'll always have those same arguments. If you can get another processor supplier to adopt the technology, the conversations become a lot easier. Right? We've had conversations with each one of them. There's been no adoption by them, but the conversations are still being had. The other thing that we're trying to do with OpenCAPI is there's an initiative in the industry today to come up with a common accelerator architecture. And it's being done in a couple of different formats. OpenCompute is one of them. That's one, and there's another one called there's like an open accelerator platform as well. And they want an architecture to basically become the standard for folks to basically develop their accelerators on. We're trying to see if OpenCAPI fits that bill or not, right? Because if you can solve it through an industry initiative versus just being IBM the lone voice, the arguments become a lot easier. And so we understand that. We want to be part of the open initiative kind of conversation piece, I guess you could say. Otherwise, it is difficult when when IBM tries to lead the charge. So if you could get one of those other guys to adopt it, that makes it a lot easier. So.